We have Dr. Sook-Lei Liew, assistant professor at the University of Southern California with joint appointments in the Division of Biokinesiology and Physical Therapy, the School of Medicine Department of Neurology, and the Department of Biomedical Engineering. Dr. Liew archived the anatomical tracings of lesions after stroke, or the ATLAS data set that you've heard about earlier, with ICPSR originally in 2017 and updated in 2018. One of the ATLAS team members presented an overview of that study, also in Chicago with us, with the early intervention folks.
All right, thank you. So I'm going to talk about, and thanks to Ken and Shane for discussing it a little bit already. We actually archived some brain imaging data that we had for stroke brain imaging with manual lesion segmentations. I'll start with the rationale. So I think, as we all know, there's a lot of interest in using large data for precision rehabilitation. So being able to mine that data and use machine learning or other algorithms to develop predictive models of what types of treatments would be best for a specific person or what their prognosis is likely to be. And especially when you have a diverse kind of population, which I think is basically all of rehabilitation, it's great to have larger heterogeneous data sets because that allows us to capture data trends that can generalize to the wider population. Because of this, one of the main focuses of my research lab is on data meta-analysis. I'm the chair of what's called the Enigma Stroke Recovery Working Group. We are one of, I think, 28 working groups in the Enigma Worldwide Consortium that focuses specifically on stroke. And so the other groups focus on depression and Parkinson's and other diseases. In Enigma Stroke Recovery, we currently have over 100 researchers contributing data, their secondary data, and they're coming from across 32 research sites across 10 countries. And this actually is exciting because it's something that's been growing more and more. I think one of the sentiments that's been expressed is that the emphasis on data sharing now has become greater, and so people are looking for how to share their data and how to pool it together so it's more powerful. What we get is usually MRI data from stroke patients as well as behavioral data and demographics. We sometimes call ourselves a goodwill of data. So people will do their study, whatever they were, got a grant to do, collect their data, and then they just dump it to us. We do a lot of the data curation ourselves and have to sift through what's usable and what's not usable, and then we can meta-analyze that. And by doing this, I think most stroke brain imaging studies have about 20 to 30 subjects, but in our data set together, we have over 1,800 subjects now and growing. So it's been a great data set to work with. The biggest challenge that we've had, though, is that for stroke research, we do need to manually segment the lesion. So after a stroke, you have damaged tissue, and that damaged tissue should be largely responsible for a lot of the behavioral impairments that you see. And so we need to characterize that, and what we have to do usually is we open up the brain image and we manually trace slice by slice the lesion outline. And so you just have to know your neuroanatomy and know what is a lesion and what isn't a lesion. In a small lesion, it can take a few minutes. In a large lesion, it can take 4 to 6 hours. So it's not really a scalable process when you start going up to thousands of brains. So we had this question of how can we scale lesion segmentation for thousands of brains, and our approach took 3 steps. The first is we manually created and archived a large data set for testing and training different machine learning algorithms for segmentation. And then that's kind of what we did here and with Atlas. And then I'll talk a little bit more about the use of it. So we've been able to apply machine learning algorithms to this data set. It serves as now kind of like a standardized evaluation metric for a lot of algorithms. And it's being used to create new algorithms. And I'll talk just briefly about how we're also trying to crowdsource efforts to improve this data set so that it's an evolving data set. So that as we get new data in, we can do lesion segmentation and have crowdsourced efforts to improve our segmentations and then recontribute that back as future Atlas data sets. All right, so just to talk about the archive itself, I think one of the questions, as has been mentioned, is why publicly archive stroke brain imaging. Most people, as you know, it's pretty expensive. It's about $600 per scan per person. So when you get brain imaging, you try to keep it to yourself and mine it for all it's worth. But for us, like I said, the big problem is trying to develop better algorithms for being able to automatically segment the lesion. And that uses machine learning, and machine learning uses a lot of data, or requires a lot of data to train the machine to do the accurate segmentation. Existing public data sets are about 30 to 60 subjects in them, and those already were pretty large. That was what was being used in international lesion segmentation challenges. And so most researchers, if they are on methods development and developing algorithms, they just use the data they have on site, which is usually about this size. So it's a huge limiting factor for algorithm development. So we decided to create and release our data set, so that would be the largest open source heterogeneous data set. In a sense, we considered this outsourcing part of our work to the general scientific community. So we created the data set, but we wanted other people to use it to create better lesion segmentation algorithms that we could then use again. So this is just a video showing the overlap of all of the lesions in purple on top of a 3D brain. We ended up releasing 304 stroke T1-weighted MRIs with manually hand-segmented lesion masks, along with neuroradiological evaluation data and metadata through ICPSR. Our process, like everyone said, has been wonderful. That was our first time to archive data, and I think it was ICPSR's first time to use brain data. So we both learned a lot in the process, and I thought ICPSR and CLDR were so gracious about learning about our data format and what's needed and how to support that. It was a really wonderful process, and I think the whole process of data curation was also very useful to us. We actually then released the data secondarily on a neuroimaging data archive, where most of the brain images go. So it got a second life there as well. And then we did publish about this data set on Nature's Scientific Data, and I think that really helped to drive a lot of attention to the data set so that people were interested in using it. So our goal with this data set was to improve the rigor, quality, and reproducibility of stroke MRI research so that people can analyze their lesions robustly across different sites. What it took was a team of 11 people in my lab, fed mostly on tacos, tacos and pizza, to trace these lesions, which took about 1 year. They had to trace, and then 2 people checked each lesion as well. It was a pretty rigorous process. The impact of Atlas, so the paper came out in February 2018, so it's been about 2 years now. We've had a lot of good attention to the data set. I think it's pretty rare, especially to share this type of data, and so we've had over 8,000 article views, like they said, 2,000 data downloads from ICPSR, 800 that came to us from our other neuroimaging website. And the most common uses, of course, are to develop or test machine learning algorithms for automated lesion segmentation, which is what we were hoping for. But it also kind of takes a life of its own, which is something I appreciate about releasing and sharing your data, is that I think, as has been expressed already, once you put it out into the public, people can use it in ways that you wouldn't have imagined that are so exciting and really extend the life of that work. So one thing is that it's been used for a lot of educational projects. I think, as Vera mentioned, is our data is commonly downloaded by the Stanford machine learning classes, especially for the computer vision classes, because lesion segmentation is a really challenging problem. So students are using it. It's becoming a part of thesis and other manuscripts. It's been cited, I think, about 35 times so far. And it's become also one of the benchmark data sets for lesion segmentation, which is nice, because that helps us to know kind of what's out there and what we could use. So in terms of the machine learning algorithms, we've done a few things with this data set. The first is that we took it once it was done, and we evaluated ourselves all the publicly existing algorithms that are out there. There were only actually 3 that are publicly available. A lot of people have their in-house code that they're not willing to share. And so we evaluated them and found one that performed the best, which was called Linda. It's a supervised machine learning algorithm, and that's actually what we started to use on the remaining 1,500 scans in our data set. So we use that on it. The problem, though, is that Linda only has an accuracy of about 50%, which is really not very good. And it takes a long time on a powerful computer. And more recently, a new type of machine learning, deep learning or convolutional neural networks has come out, and that uses a lot of data, but it has been a much more powerful approach. So these are some of the papers that have come out using our data set, using UNets or XNets or parallel capsule, all sorts of networks to try to evaluate the data. We actually we look at the papers that have cited it and go through and look at what their accuracy report is with our data set, and then we contact them when they're good. So for instance, this paper came out and said they had over 90% accuracy, so immediately emailed them and asked them for their code and told them that we have more data in our lab that we haven't released that we'd like to test on. They just shared that with us, so we're testing it now. So I'll let you know. Some other things we're doing with it. So because a lot of people like to publish about it, but they don't want to share their code because that's proprietary, we are working with a team in Paris using a RAMP model. It's Rapid Analytics and Model Prototyping. We're going to create a challenge website so that people can actually collaborate on creating new lesion segmentation methods. And they have to work together collaboratively instead of competing and upload their code for the segmentation, and everything gets evaluated on the back end. The other uses, some people have come out with a novel stroke probabilistic atlas using our data, which wasn't really an intent. I think there's also now a 3D printed head model that uses our data for something. We're also using it to evaluate, for instance, other types of methods that aren't necessarily related to the lesion, but people want to test their methods in stroke data. So it's become a rich data set for that as well. Lastly, just one thing that we're doing to kind of complete the evolution of this is crowdsourcing some of the efforts. So right now when we get data in Enigma, people will just email us or transfer us their brain MRIs and their behavioral data. We process that data and we run Linda because that's the current best performing algorithm that we have access to, but we're happy to replace that with another algorithm. Then we have to visually inspect and manually correct the lesion output still, and then we can process the data and do our actual analyses. So as you can imagine, this has now become our bottleneck, is the manual inspection of the data. And so we have to go through and look at thousands of brains, and it's very tedious and boring. And so we have come up with a solution that found an unlikely inspiration from Tinder. So I don't know how many of you are familiar with Tinder, but it's a dating app on your phone, and you're shown pictures of people that you might like to date, and you swipe right if you'd like to date them and left if you wouldn't. The beauty of it, though, is that it's supposed to be a quick, easy process to make a decision. So we came up with what we call Brainder lists. The list stands for lesions. This was created with my collaborator, Anisha Keshavan, and she originally created one called Brainder, where you just swipe right or left on MRI images based on quality. So if you see head motion or artifacts, you swipe left, and if it's good quality, you swipe right. And we adapted it for lesions. So you have a blinking GIF, as you see here. That's the lesion mask that was outputted by the segmentation algorithm. If it's good, you swipe right. If it's bad, you swipe left. The idea is to make it fast and easy for people to go through lots and lots of brains. We've tried to gamify it, so we have a leaderboard. I think at the current top of our leaderboard is a 11-year-old who has a lot of time and a great interest in brains. But anyone can play it. We've tried to get our family and friends to play it, which actually does not make you that popular. But you can also unlock levels as you do more swipes, and there's a tutorial, of course, so you get feedback about how you're doing. It teaches the public a little bit about brains and brain health, and it also gives us, through this process, we've gotten quality control ratings on over 17,000 times. So given that there's, I think, about 1,200 MRIs in there, that means each one has over 10 to 15 votes. And then we use machine learning on that to identify the ones that we need to go back and manually segment versus the ones we can just pass and move on with. So in the total picture, I think our future direction is a complete lesion segmentation pipeline that would be super useful for us because we have a lot of data, but I think also useful for any research group that's doing stroke brain imaging, because we get now asked questions a lot about lesion segmentation, even for 10 or 20 subjects, and it's a somewhat subjective process. So we'd like to be able to apply machine learning to almost the entire pipeline. and then only have to manually correct the failed lesion masks after they fail brainderless. And then all the lesions will go back into a repository, and we will release that as a new data set. And it becomes kind of a life cycle so that the data set continues to grow. And as the data set grows, the algorithms should also improve. So that's our long-term goal. But thank you so much for your time and also for the funding from CLDR. I'll take any questions. Yes.
So I was getting a lot of inspiration from what you're doing and wishing that I had been born maybe 40 years later. But because you're doing such creative work. But I also was, you and I were talking earlier because I have a large data set. Oh, thanks. I have a large data set of videotapes of faces in Parkinson's disease that we have done fax coding, facial affect coding on, and looking at intensity of different actions in the face and that sort of thing. And there's a lot of similarity, but I'm dealing with the idea of should we ever put it into a database because of identifiability.
Right.
And even though people had said, okay, most of our participants said, yes, you can use our data. And it was in 2013 that they signed a consent form that said, check the box if you don't mind us using it in education or other research.
Right.
And so anyway, you have dealt with identification yourself.
That's right, yeah.
And so I'm just interested in how you did that.
Sure. So with ICPSR, we actually developed a more rigorous access point. So they actually have to download a full written agreement and sign that. And it says that if they can identify any of the participants, they should let us know and also delete it. And so there's kind of a clause in there for identifiability. With the other data set, the subset that I released with the neuroimaging archive, they don't have as stringent rules, and they weren't willing to do the same agreement. So we had to deface the MRIs, which is we kind of like scrub off the bone structure, I guess, on the face, so that you can't reconstruct a face from those images. But it makes it a little hard to process with. For faces, you can put definitely, I think ICPSR will work with you on ethics and clauses. You can. I mean, that is a very rich data set that I think a lot of machine learning communities would be interested in. You can also, I think, identify who you would like to be your users. We opened it up to everybody because of our intention for it, but I think in that case, you may want to only release it to academia, for instance, versus to industry or something like that. So I think you can put, I think Amy can speak to this better than me, but you can put all sorts of permissions on and restrictions on how you'd like the data to be used.